We are going to talk about chapter 6 today, which is circulation modes. Wow, there is a lot here. We're going to talk about the Southern Oscillation and El Nino, the North Atlantic Oscillation, the Northern Annual Mode, the Southern Annual Mode, the semi-annual oscillation, the North Pacific Oscillation, the Pacific Decadal Oscillation, the Atlantic Multi-Decadal Oscillation, Southern Hemisphere Wave number 3 pattern, the Madden-Julian Oscillation. It has been known since the work of Sir Gilbert Walker in the 1920s that there are major large-scale oscillations within the general atmospheric circulation. Walker described the famous Southern Oscillation in sea level pressure across the equatorial Pacific Ocean, the North Atlantic Oscillation between the Azores high pressure cell and the Icelandic low, and the North Pacific Oscillation between the North Pacific high and the Aleutian low. Each of these involves a seesaw in the pressure gradients between the respective centers. It has subsequently been shown that there are many others, including the Northern Annual Mode and the Southern Annual Mode, between northern and southern middle and high latitudes, respectively. The identification of these oscillations became possible when there were extensive series of daily pressure and geopotential height data. Now, indices of the principal oscillations are routinely updated by NOAA. In the North Pacific and North Atlantic, there are long-term oscillations in sea surface temperatures. Different modes of these oscillations can persist for months to years, and they exert a major influence on regional and global climate, modifying storm tracks and the distribution of climatic anomalies. The Southern Oscillation is a fluctuation about negative to positive millibar in surface air pressure between the equatorial eastern and western Pacific Ocean. Its strength is measured by the difference in MSL pressure between the subtropical high over Haiti and the equatorial low over Darwin, Australia, referred to as the Southern Oscillation Index, SOI. The inverse correlation coefficient between these two remote pressure centers is about negative 0.8, meaning that when pressure is high in one center is low in the other. This phenomenon of distinct correlations in atmosphere conditions is known as a teleconnection. There are many such teleconnections in the atmosphere. Teleconnection. Between 1909 and 1930, Sir Gilbert Walker described correlations between atmospheric pressure, temperature, and rainfall anomalies at great distances, 3,000 to 6,000 kilometers. However, some of these correlations were later found not to be robust over time, and interest waned. In 1935, Armstrong proposed the term teleconnection for spatial patterns of climatic fluctuations. The term was adopted by J. Jerkins. Armstrong proposed the term teleconnection for spatial patterns of climatic fluctuations. The term was adopted by J. Perkins in 1969 to refer to patterns of circulation in the equatorial Pacific. Renewed attention was given to them in the 1980s and 1990s when a large number of patterns was identified. In winter months in the northern hemisphere, correlations range from 0.72 to 0.86. Figure 6.2 illustrates the 5 most prominent in the middle troposphere. A variety of statistical methods are now used to identify the patterns. The southern oscillation in the atmosphere has a time scale of the order of 2 to 3 years. It is closely coupled to variations in tropical Pacific sea surface temperatures, typically when the SOI is large, with stronger high pressure in the eastern tropical Pacific. The Eastern Ocean is cool, with strong oceanic upwelling, and the Western Pacific is warm. The upwelling in the Eastern Pacific is caused by persistent easterly trade winds pushing the surface water away from the coast of South America at about 3 to 7 year intervals. The trade winds weaken and the Eastern Pacific warms, often around Christmas, and the pattern of vertical zonal circulation south over the Pacific Ocean shifts eastwards as pressure rises over Indonesia. The warm southward flow ocean current of Peru is called El Niño, Spanish for the Christ trial. The opposite cool mode is known as La Niña, the girl, associated with the cool, north-flowing Humboldt or Peru current. These two phases of the couple El Niño Southern Oscillation ENSO patterns are shown here, and the ocean conditions of each plate. So El Niño and La Niña are the source of the greatest climatic anomalies on Earth. In Peru, with El Niño conditions, there are heavy rains that often cause landslides in the mountains. The offshore upwelling ceases, water temperatures rise, and the fisheries collapse. The Pacific Northwest and Alaska is enormously warm, and there are drought conditions in eastern Australia, southern Asia, and Mexico. In El Niño years, there are fewer West Pacific tropical cyclones over Guam, and there is also cyclone activity in the tropical Atlantic during La Niña. There are strong easterly trade winds across the tropical Pacific Ocean, and in Indonesia there is low pressure and a strong vertical convection, giving rise to wet weather. The low-level easterlies in a vertical motion generate an upper-level westerly return flow that makes up one cell of the so-called wet east zonal worker circulation. There are two other corresponding cells over Africa and the Indian Ocean, and South America and the Atlantic Ocean. The persistent strong westerlies over the Pacific Ocean raise sea level in the western Pacific Ocean by about 60 centimeters as a result of wind stress on the ocean surface. La Niña patterns give rise to wet conditions in the Pacific Northwest of South America and dry conditions in the southwest and southeastern United States and in the west central Pacific. Northeastern South America tends to be wet. Both ENSO modes appear to be closely linked to the annual cycle, tending to develop in boreal spring and lasting at least a year. There appears to be a close coupling between the atmosphere and ocean. In March-April, there is a peak in the occurrence of low-level westerly wind bursts WWBS lasting 7 to 10 days in the western equatorial Pacific. Many of these WWBS seem to result from the simultaneous presence of tropical cyclones in each hemisphere, giving westerlies along the equator. The WWBs set up very long wavelength ocean Kelvin waves that across the Pacific to the east in 3 to 4 months and lead to warming of South America. So the North Atlantic Oscillation, NAO, is oscillation in sea level pressure between the Azores subtropical anticyclone and the Icelandic low pressure center. When the pressure gradient is large, the NAO index is positive and there are strong westerlies. And when the gradient is reversed, the index is negative and the westerlies are disrupted. The NAO is the dominant mode of winter climate variability in the North Atlantic sector. During extreme negative NAO events, there are typically well below normal temperatures in northwestern Europe and above normal precipitation in the western Mediterranean. Also, there are above normal temperatures in western Greenland and below normal temperatures in the western United States. The NAO determines the strength and direction of the mid-latitude westerlies and the storm tracks across the North Atlantic. In positive NAO winters, there is more precipitation over northern Europe, and the Mediterranean is drier. The opposite occurs in negative NAO winters. The NAO index varies in intensity and sign, but does not exhibit any periodicities. The index was largely positive from 1900 to 1950, negative in the 1960s. That has been mostly positive since 1970s until about 2006. The Northern Annual Mode, also known as the Arctic Oscillation, involves low pressure over the Arctic Ocean and high pressure in mid-latitudes, positive mode, or vice versa, negative mode. It is represented through the troposphere. Thomson and Wallace first described it and showed that high index shown in AM days feature westerly surface winds along 55 degrees north and transfer flow from Russia towards Canada, where low index conditions are marked by cold anticyclones centered over central Canada and Russia, and an anticyclonic surface circulation throughout the Arctic basin. High index days are on average 5 degrees Celsius warmer much of the Midwestern United States. Central frequency over North American, Europe, Siberia, and East Asia under low NA index conditions. The MIS was mostly slightly negative from 1950 to 1990, and then mostly